In this video, we'll look at how to do calculations with Markov chains. There's an endless variety of calculations we could do, and all of them come down pretty much to the two basic ideas. Let's work through an example so you can see how these ideas come into play. After this example, you should try out some of the exercises. They'll ask all sorts of different questions, for example, the probability of an epidemic dying out, or the expected rate of return in a betting game. All the questions ask for different things, but the calculations all hinge on two basic properties of Markov chains. We'll work through an example calculation first, and after you've seen it, we'll highlight those two basic properties. Let's work through this example, my Cambridge weather simulator. Here's the state space diagram and the transition matrix, and the question asks us, if it's grey today, what's the chance of rain 2 days from now? In other words, if x0, x1 ... is the Markov chain, what is the probability that x2 equals rain, conditional on x0 equals grey? For the first step of the calculation, I'm going to condition on the value of x1. This is using the law of total probability. Here's the law of total probability written out as a general rule. There are actually two standard ways to write it. The first form is for calculating a plain probability, the probability that random variable big A takes some value little a, by conditioning on all the ways that it might happen, say on all the values of some random variable b. The second form is for calculating a conditional probability. We can condition on b just like before, and all we have to do is carry this baggage, the condition big C equals little c. We have to carry it around with us in each of the terms. That's what I used up above. I used the law of total probability, and I carried the baggage x0 equals g around in each of the expressions. Next step, I'll simplify the first term. This term is the probability for x2 conditional on x1 and x0. But the whole point of a Markov chain is that x2 is generated directly from x1, and once we know x1, x0 is irrelevant. We call this memorylessness. The next step is just rewriting. I've rewritten the two probabilities in terms of the transition matrix P. The first term is the probability of going from x to r, P sub xr, and the second term is the probability of going from g to x, P sub gx. Finally, just a bit of algebra to tidy up. The formula we've got looks a bit like matrix multiplication, so let me write it out like that. The property we just calculated is the p squared matrix, rho g, column r. In fact, there's a general result here. The probability of going from state I to state j in n steps is given by the relevant entry of the transition matrix p raised to the power of n. Okay, so that's a typical calculation with a Markov chain. Let me step back and highlight the two key steps here. The first key step is memorylessness. That's the defining feature of Markov chains, the idea that the next state is generated based only on the current state. So, if we know the current state, we can throw away the past history. The next key step is something that's almost too subtle to spot here. The rule for generating the next state is the same at every time step, which is why we use the same P matrix for the transition from x1 to x2 as for x0 to x1. I call this resetting the clock. We only used resetting the clock in a very simple way here. The next example will show a clever use of the same idea. This is a question about what's called hitting probabilities. I'll give you a moment to read the question. It asks us to find pi x, the probability that, starting from page x, the random surfer hits my web page, page 0, before hitting Twitter, page 5. Let's start by turning this into a question about Markov chains. Let xn be the page that the user is on after n clicks. The problem says that from each page they select an outgoing link at random, which means it's a Markov chain. Remember, the defining feature of a Markov chain is memorylessness, i.e. what you do next depends only on where you are now, not on the past. Actually, to be technical about this, a Markov chain is an infinite sequence and it's not allowed to just stop. So we need to add an edge from page 5 back to itself, and then we have a proper Markov chain. Now, let's write out what it is that we're trying to calculate. We want pi subscript x, the probability that, starting from state x naught equal x, the Markov chain x eventually hits 0. To calculate this, first thing I'll do is use the law of total probability. I'll condition on x1. This is the same sort of trick I used in the last example. One little catch, this equation applies for all states x other than 0 and 5, where I already know the answer. I know that pi naught equals 1 and pi 5 equals 0. The next step is to use memorylessness. That's why I did the conditioning in the last step. I know I can use the memoryless property if only I have x1 in the condition. It wasn't there originally, so I had to bring it in using the law of total probability. Now we have x1 in the condition, and therefore I can ignore x0 using memorylessness. I've also bunged in the transition matrix entry here, pxx1. The next step is interesting. I need the probability that x hits 0, given its value at time 1. For this, I can reset the clock. If I start it in some state at time 1 and look at the future, it behaves exactly the same as if I had started it at time 0 in that state and looked at its future. This means that the first term is nothing other than pi x1, where pi is the collection of probabilities we're trying to calculate. What we've produced here is a recurrence relation about the values of the pi vector. It looks rather like a matrix multiplication formula, and so let's write it in matrix notation. We've shown that any pi x is simply the p matrix, the matrix of transition probabilities, times the pi vector. Actually, one small correction. The algebra we just did applies to all states x apart from the two we're interested in. We know that pi naught equals 1 and we know pi 5 equals 0. We can encode those equalities by tweaking the matrix equation. I'll replace the top row of the matrix by all zeros and the bottom row by all zeros, and say that the left-hand side is equal to the modified matrix times pi plus a constant vector. This is all just bookkeeping to be able to write all of our equations in a simple matrix form. The nice thing about matrix form is that it's much easier to program a solution that way. Here's my code. First, I need to get the transition matrix P. I coded in the adjacency matrix for the graph, and I use that to get the transition probabilities. All this code does is it says if there are n links going out of a page, then each link should have probability 1 on n. I always like to do a sanity check when I'm doing computations with Markov chains. Each row has to sum to 1. In other words, from every state, the sum of the probabilities of all the possible transitions you can make out of that state must be equal to 1. Next, I'll set up my matrix equation. Let's write it as pi equals q times pi plus b, where q is the p matrix but with the top and bottom rows zeroed out. Next, I'll just rewrite it in the form that NumPy expects for linear equations, matrix times unknown vector equals constant vector, and then it can solve it for us. Okay, so that's how we do calculations with Markov chains. It may seem a bit mysterious the first time we do these calculations. How do we know what step to take next in the algebra? In the next video, I'm going to talk through the right way to frame these sorts of questions via the causal diagrams, which should give you some guidance about how to approach any sort of probability calculation. It will help with Markov chain problems. It will be especially useful for tricky Bayesian calculations.